Okay, let's see if we can work through this together. It is an important kind of problem to be able to do. It's getting at the kinds of things we want to be able to think about a lot these last 4 weeks of class. So we're thinking about the ring Z5X. So that means that's the ring of polynomials whose coefficients come from Z5. So you always want to reduce the coefficients mod 5, not the powers, but the coefficients. And we're thinking about this principal ideal generated by x squared plus x plus 2. So what does that mean? That means it's, as a set, it's the set of all polynomial multiples of x squared plus x plus 2. All polynomials that have x squared plus x plus 2 as a factor is what this represents, as well as the zero polynomial, because if you multiply by 0, you get 0. We want to find the multiplicative inverse of 2x plus 3 plus I should have said a little bit more here, in the factor ring Z5x mod I, right? Because we're talking about a left coset there. We're talking about an element of the factor ring. Z5x is certainly a ring. It's a ring of polynomials, but it's not a field. The only units in Z5X are going to be the, the constant polynomials 1, 2, 3, and 4. But when I mod by this ideal, well, I haven't said for sure it's going to be a field, but perhaps it's a field based on the theorems in chapter 14. If I is maximal, based on that definition that you read about, I know that's a hard definition to understand, then this would be a field. But assuming it's a field, this would have an inverse. So we're trying to find an inverse of that in this possible field. Even if it's not a field, this still might have an inverse. Because in rings, some elements are units, just not necessarily all of them. So the key to doing the calculations, I mean, you could think about what I have down here initially as what you need to think about doing. Set the product of this coset with an arbitrary left coset equal to the unity, right? 1 plus I would be the unity. But wait a minute, why do I know I could get away with some ax plus b here? Couldn't the coset representative have to be like something involving x cubed, for example? I didn't explain why I can get away with an ax plus b. Do you remember based on the reading? Why we can get away with a linear polynomial here? Yeah, it turns out the degree can't be higher than this because based on the reading, I mean, I'm not proving this by any means, but based on the reading, based on the calculations and the examples in the reading, when you've got a certain, when your ideal is generated by a polynomial, for example, of degree 2, and you do calculations in this factor ring, effectively you're trying to find remainders when you divide by this thing. And those remainders are either going to be degree 1 or degree 0, or in fact the 0 polynomial, which again technically has an undefined degree. That's why you can get away with this. I know that's maybe not a full explanation if you're not, and it's not a full explanation, and maybe you're not remembering from the reading that that's the case, but that is true. And the book does justify it with some examples. So we want to solve this for A and B. And so initially you'd multiply it out like this. How do you multiply cosets? You multiply their representatives. Fundamental thing to know for exam 3. To multiply these two cosets, multiply their representatives. So I have to do FOIL on these two things. So I get 2x times ax would be 2ax squared. 2xb and 3ax, or 2bx and 3ax. It looks like I made a mistake here, didn't I? 2bx and 3ax are the outside and inside terms. And last times last would be 3b. So you multiply cosets by multiplying their representatives. That's the definition of coset multiplication in factor rings, and that's the thing that becomes well defined when you assume this is an ideal. That's the way the definition of an ideal is constructed, is to make that happen, to make that well defined. So you're wondering, how do I choose A and B so that this equals 1, or is equivalent to 1 at least? It's helpful to replace x squared with 4x plus 3. That's where this calculation comes into play. You want to use, well, the fact that these are the same. And why are those the same? Well, because x squared plus x plus 2 is an I. So this is the 0 coset. For extra emphasis, I could say this is 0 plus I. It's not the unity, it's not 1 plus I, it's 0 plus I, the additive identity, not the multiplicative identity. And effectively, to get from this line to this line, effectively I'm subtracted x from both sides and subtracted 2. Really, I subtracted x plus 2 plus I from both sides. But the I, it always just is there kind of as a placeholder to remind you it's a coset. It doesn't really get involved in the calculation. We're always adding and multiplying representatives. And then since we're dealing with mod 5 arithmetic, I can replace -1 with 4. I can add 5 to it, and replace -2 with 3. Add 5 to -2 to get 3. So I can replace x squared with 4x plus 3 in this factor ring. And that can simplify things, because you can get a linear representative here, and you can get essentially 2 equations and 2 unknowns in the unknowns A and B. So multiply this out. 2a times 4x would be 8ax, but remember mod 5, that's going to be 3ax. Plus 2a times 3 is 6a. Mod 5 is just plus a. Everything else is still the same. Again, we're doing mod 5 arithmetic. Group together the like terms. The ones involving x, 3ax plus this. 3a plus 3 is going to be 6a, or just a mod 5. Then we have a 2b. And then your constant terms are the a and the 3b. I'm setting this equal to, I want this to equal that. So I get a system of equations. I need to solve a plus 2b equals 0 and a plus 3b equals 1. System of linear equations in the unknowns a and b. I'm looking for solutions for a and b that are either 0, 1, 2, 3, or 4. And I needed to think about doing calculations mod 5. So, I mean, you could just experiment to see if you can find anything, but you also could solve it in the usual way, being careful. For example, I could subtract the top equation from the bottom equation. As one calculation I could do. I could do a plus 3b minus a plus 2b. That equals b, but it also equals 1 minus 0 is 1. So evidently b must be 1. And if I choose b to be 1, what should a be? Well, I could use this equation. A equals -2b. -2 times 1 mod 5 is 3. Evidently a better be 3. It's probably worth checking that a equals 3 and b equals 1 satisfies the second equation as well. I have to check. If A is 3 and B is 1, yes, the second equation is satisfied as well, mod 5. Again, we're modding by 5 because we're thinking about going back to the original problem, Z5X. So it looks like the answer is that the multiplicative inverse of 2x plus 3 plus I, that coset, is 3x plus 1 plus I. As another check, let's check that. Multiply them and just double check that it works. 2x plus 3 plus I times 3x plus 1 plus I. Foil the representatives, you're going to get 6x squared plus, I'm not modding by 5 initially, I got a 2x and a 9x is an 11x plus 3. Yeah, we can mod by 5 right away, but that doesn't finish it yet. What finishes it? How do I know this is the unity coset? I've got to do the same trick we did way back up here. Replace x squared with either negative x minus 2 or 4x plus 3. Replace it with 4x plus 3. Gives me 5x plus 6 plus I, but now mod by 5, and that's 1 plus I. Done. And this was the kind of thing that I was trying to convince you last Friday that can be kind of fun once you really get into it enough and the initial confusion is dispelled. These kind of calculations are supposed to be the fun part of the course here. Proofs maybe not so much as a fun part of the course. Can I clarify anything? Mm-hmm. Yeah, that'd be another way you can do it. Yep. And that emphasizes another good point. So let's see, what were you saying? Were you looking right here? Yeah. So essentially you're saying, and looking at this, to think of that, yeah, exactly, as x squared plus x plus 2 plus 1 plus I. Exactly. Yeah, that's it. That's even more fun, perhaps. And then, yeah, giant slurping sound. X squared plus x gets sucked into I. And you're left with 1 plus I. Why did it get sucked in? Because it's how I is defined. And in fact, it's not just x squared plus x plus 2 that would get sucked in, but any multiple of that would get sucked in because it's an ideal. I think it would be worthwhile now to continue looking at some things in the reading from chapter 14 and make sure you really understand as much as we can here. Pretty important chapter here, chapter 14. Let's look at the parts of chapter 14 about prime ideals and maximal ideals. So again, here's the definition of both a prime ideal and a maximal ideal. It's a hard concept here. I always kind of struggled with both of these concepts when I was learning this material. But it's going to be important for us, and definitely examples help. Okay. So a prime ideal A and a commutative ring R is a proper ideal. So that rules out the entire ring. The entire ring is an ideal in itself, but we're talking about proper ideals here. So that if A and B are in A, that implies either A is in A or B is in A. Why is this called a prime ideal? This is supposed to be analogous to Euclid's lemma actually. If P is a prime and P divides A times B, then P divides A or P divides B. And in fact, if you think about example 13, the proof that this is a prime ideal if and only if n is prime is essentially Euclid's lemma. Let's think about it here. The claim NZ, which represents all multiples of the integer n, and would be the same as the ideal generated by n, the principal ideal, and also the same as the cyclic subgroup generated by n. But remember, principal ideals and cyclic subgroups don't typically match. They match for z. This is a prime ideal where a background assumption here is that n is greater than 1. The trivial ideal actually is a prime ideal as well, but we don't want to think about that here. It's a prime ideal of z if and only if n is prime. Let's think about proving this direction of the backwards direction. And instead of calling it m, let's call it p. Suppose p is prime. Why is pz a prime ideal? Well, you got to go back to the definition of a prime ideal. Does A times B being in the ideal imply either A is in the ideal or B is in the ideal? Suppose A times B is in PZ. What does that mean? That means then there exists an M in Z such that AB equals MP, right? Or PM. In other words, P divides A times B. But now Euclid's lemma comes into play from chapter 0 to imply P divides A or P divides B. And that in turn means, if you think about it carefully, that either A is in PZ or B is in PZ. And that's enough to prove that PZ is a prime ideal. Okay. What's a maximal ideal? A maximal ideal, first of all, again, has to be a proper. Can't be the entire ring by definition. Such that whenever B is an ideal that satisfies these inclusions, A is a subset of B is a subset of R, then either B is equal to A or it's equal to R. It can't be something in between. Visual. If there's your ring, and if A is a maximal ideal, there can be no ideal, no proper ideal of R strictly containing A if A is maximal. There's nothing, if I draw a dashed blob containing A, and also that's a subset of R, it can't be an ideal. Once again, examples help. It's easiest to think about with finite examples like Z36. In Z36, the principal ideal generated by 2 and the principal ideal generated by 3 are maximal ideals. And we're talking about in Z36. What are these principal ideals? If you wanted to figure out what they are, well, the principal ideal generated by 2 would be all multiples of 2 mod 36, which is also, just like with Z, the same as the cyclic subgroup generated by 2 under addition. Cyclic subgroups and ideals, principal ideals, are going to be the same in Z, but also in Zn. These are the things, all the things you could get by multiplying 2 by anything in Z36 and then modding by 36. You're never going to get an odd number. And it's the same as the cyclic subgroup generated by 2 under addition. Add 2 to itself over and over and over again, you're going to get this same set. Principal ideal generated by 3 is going to be all multiples of 3. Mod 36. Those are not the same thing. Sets, certainly there is some overlap between them. These are maximal ideals. There's no proper ideal in Z36 that properly contains either of these. All the ideals in Z36 are principal ideals. They can all be generated by a single element, which makes an intuitive sense because Z36 as a group is cyclic, and the only subgroups, cyclic groups, are themselves cyclic. This lattice of subrings, ideals, really is the same as the subgroup lattice you would get if you were only thinking about group theory, if you're only thinking about addition. This is a subset of that. For example, all multiples of 4 are also multiples of 2. So all multiples of 6 are also multiples of 2. All multiples of 9 are also multiples of 3. And you can continue. These are all the ideals in Z36. Of course, they're not the unique ways of representing these ideals. These are not the only representatives, so to speak, generators, you might call them. And 2 and 3 are proper, and they are maximal. They're the biggest. They're not the same size as each other. Maximal doesn't mean absolute biggest ideal in terms of number of elements. It means maximal with regard to this condition. Then we got these theorems here. Oh, I did want to talk about example 15 as well. Let me talk about the theorems first. We got these theorems that are pretty important. The context of both theorems is you're in a commutative ring with unity. So we're only applying this to commutative rings with unity. In such a ring, when the factor ring is an integral domain, that's equivalent to the ideal being a prime ideal. And when the factor ring is a field, that's equivalent to A being a maximal ideal. Though remember, last week we did talk about how finite integral domains are automatically fields. Do you remember that? Remind yourself, what's an integral domain? An integral domain is, for us, is a commutative ring with unity in which every non-zero element is not a zero divisor. It's got no zero divisors. Integral domain is a commutative ring with unity and no zero divisors. So all the non-zero elements are not zero divisors. Not necessarily units. They don't necessarily have multiplicative inverses. But they're not zero divisors. By the way, I forgot to emphasize when talking about integral domains that the cancellation property holds. Read about that, but I haven't really emphasized that in class. This holds in spite of the fact that A might not be invertible. A might not be a unit. So integral domains are where the cancellation property holds. But a finite integral domain is automatically a field. All the non-zero elements are in fact units. So coming back here, if R happens to be not just a commutative ring with unity, but also a finite commutative ring with unity, then these two conditions are really equivalent because finite integral domains are fields. And that would mean in finite integral domains, maximal and prime ideals are the same concept. In finite integral domains. But in infinite integral domains, they're not necessarily the same concept. Or in infinite rings, if R is an infinite ring. These proofs, when you first read them, feel probably kind of tricky and difficult. But when you really get into the working with this stuff enough, they're not as bad as they seem, especially this one's not too bad. This one's a bit trickier. Let's take a look at them. So it's an if and only if, so you need to go both directions. Suppose, first of all, that this factor ring is an integral domain. We're trying to show that A is a prime ideal. So start by assuming A times B is in the ideal and show either A is in the ideal or B is in the ideal. Without looking, let's just do a little experimentation. Assuming A, B is in A. What would that mean? What's something that would imply in, say, the factor ring that we're thinking about? What would that imply, for example, about this particular coset? If AB is in the ideal, then this left coset is, what could you say about it? It gets sucked in. This is A. This is the zero coset, the additive identity. What are we trying to show here? We're trying to show A is a prime ideal. We're trying to show either A is in A in big A or B is in big A, using the fact that this is supposed to be an integral domain, has no zero divisors. I've got a product equaling zero. Although maybe I need to think about this thing like this, as the product of these left cosets, which it is by definition of coset multiplication. And now it's set up to work. Why? I'm assuming, again, this is an integral domain, and I've got the product of two things equaling the zero coset. That means one or the other of them has got to be the zero coset. Therefore, little a plus capital A equals capital A, or little b plus capital A equals capital A, i.e., in other words, little a is in capital A or little b is in capital A. Done. That's what you wanted to prove. Because the goal was to show that capital A was a prime ideal. That's what the textbook does here. For the other direction, assume A is a prime ideal, show this is an integral domain. We need to show it doesn't have any zero divisors. It's already a commutative ring with unity, since R is a commutative ring with unity. So show it's got no zero divisors. Suppose the product of two arbitrary elements equals the 0, show that one or the other is the 0 coset. But this product right here is the same as this. The author didn't write it, but could have. So that means A times B is in capital A if this does indeed is assumed to equal capital A. But A is a prime ideal, therefore either little a is in capital A or little b is in capital A, and therefore one or the other of those is the 0 coset. The proof that the factor ring is a field if and only if A is maximal is definitely a trickier proof. And I don't think I'm going to take the time to go through it in detail here. But it is understandable. Probably the hardest part is the very last few lines here. Yeah, I'll leave that to you for the moment. Let's look at example 15 next. This one, I think is, well, it starts out not too bad, but then it gets more confusing as it goes. The claim is that this ideal, this principal ideal, is maximal in Rx, the ring of polynomials with real coefficients. Is Rx a field? R is certainly a field. What about Rx? No, it's not. In fact, rings of polynomials are never fields, never ever, even when the coefficients come from a field. When the coefficients come from a field, it's an integral domain, but it's not going to be a field. That's an example of an infinite integral domain that's not a field. Rings of polynomials are never fields because any polynomial of degree higher than 0 can't possibly have a multiplicative inverse. Claim is this is maximal. How is it done? They probably should have used the letter B here to be more consistent with the definition of a maximal ideal. Suppose you got another ideal that properly contains this. So in this picture, the A really is the ideal that's generated by x squared plus 1, and the B in the definition is played by this other ideal A. Properly contains this. We're going to prove that's actually the entire ring. That would be the strategy for showing an ideal is maximal. How? By proving something that we talked about last Friday. In fact, I had your work on it as the very first thing in class, to prove that if an ideal contains the unity, it's actually got to be the entire ring. That's a common strategy. That's why I emphasize that problem. In this type of problem, and trying to show a certain ideal is maximal by doing what they say to do here, to show the other ideal you assume properly contains it, is actually the entire ring. The most common strategy is to prove that the unity is actually in this. The details of how that's done can be tricky or hard or impossible if it's not a maximal ideal. And they actually do this by proving that it's got some non-zero real number, first of all, and that would imply that 1 is in there. C is a real number. 1 over C would be another non-zero real number. Doesn't matter what non-zero constant polynomial we find, into B and A, it just finds something. So what's the strategy here? Okay. Suppose f of x is in A, but not in this ideal. It's not clear that that's a good thing to do next. In fact, I think none of the rest of the argument is clear that it's going to lead you to the thing you want to show, that there's some non-zero constant in the ideal. But let's just try to confirm that we understand the steps. If f of x is not in there, what does that mean? It means it's not a multiple of x squared plus 1. X squared plus 1 is not a factor of f of x. That's what it means. So if we divide f of x by x squared plus 1, we have to get a non-zero remainder. This r of x here is the remainder of the division. There's your quotient, q of x, there's your remainder. You don't know what q of x and r of x are because you don't know what f of x is. But there's some non-zero remainder, and it would have to be non-zero because I'm assuming f of x is not in this ideal. Really the author's really using a division algorithm for polynomials. Right? We had the division algorithm for integers back in chapter 0. Without telling you, the author is implicitly using that. That's actually not until chapter 16, actually, that the author states the division algorithm for polynomials. So the author's playing a little fast and loose with you here and just saying, assume you can do this, essentially. Degree of r of x is less than 2, though. Just like in the division algorithm for integers, the remainder is less than what you were dividing by. Here in the division algorithm for polynomials, the degree of r of x is less than the degree of what you're dividing by. X squared plus 1 has degree 2. So r of x, if it's non-zero, has degree less than 2. Degree 0, it's either constant, or degree 1, it's linear. So r of x is of this form, where a and b can't both be 0 because then r of x would be the 0 polynomial. If you solve this equation for r of x, you can say this. Just subtract q of x times x squared plus 1 from both sides. And the claim is this is an a. That's the first mysterious thing, is why is that an a? Somewhat mysterious. Giant slurping sound. Q of x times x squared plus 1 is an a because it gets sucked in. Because a is the ideal generated. Sorry, wait a minute. A is not the same as this, so now I'm confused. Let's see. F of x is certainly an a because we're assuming it. Right, which would definitely be in this ideal here, but we're assuming a is not the same as that ideal. It properly contains it, so I'm a little confused. I thought about this before class, and I was satisfied that I understood it, but now I feel confused. Certainly, if both of these were in a, then their difference would be an a. It would be closed under subtraction. And certainly f of x is an a. But yeah, why is that one an a when a is not equal to the ideal generated by x squared plus 1? You would think by then an assumption that it's not. So I'm confused. It's funny, you probably experienced this, how you think you've convinced yourself beforehand, and then all of a sudden when you look at it again, you feel confused again. Right there? Well, f of x is in a. That's what we're trying to show. We're trying to show a equals. That's the goal, to show that. We haven't shown it yet. They're essentially saying this is the argument for how showing a non-zero constant polynomial is in A implies that A equals Rx. That's the goal. Is Q of X is not necessarily an A. Okay, well, let's skip that for the moment. If I figure it out before the end of class, I'll let you know. But if I figure it out after class, I'll send you a message. But this part I thought was the part I was more confused about initially. Though the steps are actually pretty clear. What was less clear is like, what in the world are they doing here? This product is certainly in A. Why? Oh, because of what they set up here. Up by this line right here that I feel a little confused about still. The claim is that AX plus B is an A, and A is an ideal. So yeah, any multiple of AX plus B is also an A. This gets sucked into A. And this is true because X squared plus 1. Okay, that clears up my confusion about this too here. Okay. X squared plus 1 is, okay, A properly contains this ideal. So it doesn't equal it. So there are some things in A that are not in this ideal. However, everything in this ideal is in A. A does contain it. So X squared plus 1 times Q of X is in this ideal here. Therefore, it's also an A because A properly contains it. That's the fix of my confusion. Redraw the picture here. Here's the ideal generated by X squared plus 1. Here's A is an ideal that properly contains X squared plus 1. Anything in this ideal, the smaller one is in the bigger one. We ultimately trying to show A actually equals all of R, so this picture is still not quite accurate. But initially, that's the idea. And so, yeah, this is in the ideal generated by X squared plus 1. Therefore, it's also an A. You can certainly check that this product is true. This equation is true. The real question is, why is the author doing that? The answer comes down here. Evidently, whoever first thought of this, whether it was the author or somebody else, just had to do a bunch of experimentation. A squared plus B squared, which is a constant polynomial, a non-zero constant, because either A is non-zero or B is non-zero, does equal the difference of these two things. This one minus this one. You can check that that works. The X squared terms cancel. And both of those are an A, and therefore their difference is an A. So this non-zero number is an A. And that's what they wanted to show. That's the C. It's not easy stuff, as none of this class has been. But I guess I'm trying to really emphasize this because I feel like this chapter is the key to everything that comes after this point. Really getting chapter 14 is key to not being confused the rest of the semester, or not being confused as much as you would be otherwise. Might be a better way to say that. You want to make sure you get chapter 14. Chapter 15 is about ring homomorphisms. We got group homomorphisms. We should probably also have ring homomorphisms, and in fact, we do. And it's a natural generalization of the idea of a group homomorphism. Now you've got two operation preserving properties instead of just one, because you've got two operations instead of just one. Very similar concepts to group homomorphism in terms of what's true. Properties of ring homomorphisms. This one's true from the fact that ring homomorphisms are automatically group homomorphisms. Rings are groups under addition. N times R, when N is a positive integer, means R added to itself N times. This is the group homomorphism property, back from chapter 9 or something. Here's a new one that applies to rings, though it looks the same as the old one for groups, because with groups, we assumed the operation was multiplication in the abstract. The direct image of a subring is a subring. The direct image of an ideal is an ideal if you also assume phi is onto. So that's a little bit of a thing to watch out for. You need to know that phi is onto for it to be an ideal. Are there examples of non-onto homomorphisms, ring homomorphisms, where even when A is an ideal, phi of A is not? There must be, although I can't think of any off the top of my head. Remember this? Inverse image, pre-image. You can write this symbol even if phi inverse does not exist, which if phi is not a ring isomorphism, technically phi inverse doesn't exist. But you can still use this notation, and people do. The inverse of B is called the inverse image or pre-image of B under phi. It's everything in R that gets mapped into B. Here's R. Here's S. B is an ideal in S. Phi inverse of B, when I say that, it doesn't mean phi inverse exists. It's just shorthand verbal description. I should really say the pre-image of B in R is everything in R that gets mapped into B. Which, if phi is not 1-to-1, is in a sense going to be bigger than B, but I didn't draw it that way. If B is an ideal in S, this pre-image is an ideal in A. You don't need to assume phi is onto or 1-to-1. Should be able to prove this with the ideal test. I could see that coming up on exam 3. If R is commutative, its direct image is commutative. If R has unity, and if S is not trivial, and phi is onto, then its image is the unity of S. Which would evidently imply, in such a situation, that S has a unity. As long as S is non-trivial and phi is onto, and R has a unity, S must have a unity. And it must be phi of 1. You can talk about the concept of a kernel. Kernel is still the set of elements that get mapped to 0, the additive identity. It's still the same definition, not the elements that get mapped to 1. And phi will be an isomorphism if and only if the kernel is trivial. That was a property we saw for group homomorphisms as well. If phi is an isomorphism, then its inverse function, and that will exist, will be an isomorphism. Kernels are ideals, just like kernels are normal subgroups, and we have a first isomorphism theorem as well. And it's pretty much the same as the group version, except we say ring instead of group. And we use additive notations for cosets instead of multiplicative notation. But it really is the same mapping here as the first isomorphism theorem for groups. So a lot of the concept for group homomorphisms carry over to ring homomorphisms. But there are some subtleties of places where things differ. I think example 5 is a good one to make sure you study. The group homomorphisms from Z12 to Z30 and the ring homomorphisms from Z12 to Z30 are not the exact same set of functions. One is a subset of the other. Being a ring homomorphism is a bit more restrictive. There are fewer ring homomorphisms. Yeah. It's not clear to me how much we're going to use chapter 15. We do use it from time to time. But what we're really after is the concepts from chapters that come immediately after this. Chapter 16, 17, and 18 are pretty important. And we're heading into those. Okay. Have a good day. Question? What? Which day? I don't know offhand which day. Probably more either Wednesday or Friday is my guess.